Okay, great. Thank you to the organizers for giving me a chance to give this talk, and to you all for watching it. My name is Micah Schaible. I'm from the Georgia Institute of Technology, and today I'll be talking about some recent measurements where we explore a mechanism called spin dichroism and its ability to form enantiomeric excesses in chiral amino acids. So I'm sure I don't have to tell this crowd that chiral amino acids and many other types of chiral molecules are found in many different meteorites as well as in asteroids and comets. And here I'm showing a few different amino acids that have been identified. And in the parentheses is the largest measured enantiomeric excess of these chiral amino acids. So these being the L form, there's a 20% excess in the L over the corresponding D form. Interestingly enough, when we look across a number of different sources for these chiral amino acids, we see that very often they are enhanced towards the L enantiomer. So here showing the measured excesses of L-isovaline in a number of different meteorite types, all showing an excess towards the L form, and none really showing a statistically significant excess towards the D form. So the question that we're asking here is, why do seemingly all of these primitive meteorites display the same enantiomeric excesses, or the enantiomeric excesses of the same handedness? So different forces in space which can drive enantioselectivity include several different abiotic mechanisms. The first being sort of just a chance or statistical fluctuation in the molecular populations, which lead to an enhancement in one versus the other. Now, if there's these excesses in meteorites were forming due to a chance mechanism, we would expect both L and D forms. Alternatively, amplification, there's lots of different types of mechanisms that can drive amplification of a given chirality. But all of these still require some initially small excess of one of the enantiomers versus the other. So ultimately what we're searching for to explain why all of these meteorites are pushed in the same direction is something called a determinant force, where the excesses are at least initiated by some sort of physical force that is not dependent on the environment. So different determinant mechanisms which have been explored that induce enantiomeric excesses in organic molecules include first circularly polarized light, where light from ionizing radiation such as UV light from distant stars can obtain a circular or actually really an elliptical polarization as it passes through dust clouds on its way towards our solar system. And those circularly polarized photons can induce an enantiomeric excess. Alternatively, you can get preferential bonding or catalysis on chiral surfaces. And both of these have been explored and in general produce fairly small enantiomeric excesses. A third mechanism which we are exploring in the current work is interactions of spin polarized electrons with chiral molecules. So the question that we're asking is, can spin polarized electrons create enantiomeric excesses within populations of chiral amino acids? So first, we'll just do a little bit about where we can expect these spin polarized electrons to come from. And what we're doing is we're looking at the ejection of these spin polarized electrons from a magnetized surface. So you can imagine here our sort of schematic of an iron where all of the spins within the iron, or at least the vast majority of them, are pointing in the same direction. And so when we have ionizing radiation come in, it can excite one of those electrons, which then scatters through the solid, and then can escape the surface as a secondary electron. So it turns out that because of the polarization or the magnetization of that surface, you have an unequal filling of the Fermi energy levels within the solid, and you get more or preferential scattering off of the slightly emptier levels. So that leads to then a preferential polarization direction of the emitted secondary electrons from that surface. It turns out that a spin polarized electron in motion traces out a helical path and that by reversing the substrate magnetization direction, we can also reverse the helicity of the ejected secondary electrons. So the mechanism that we're exploring here, spin dichroism, consists in coupling between that electron helicity and the molecular chirality, and exploring whether or not that coupling can lead to enantioselective damage and formation of enantiomeric excesses. So here the idea is that we have some sort of ionizing radiation come in. In these experiments we use X-rays. They excite secondary electrons from the surface, which then are ejected out and can interact with molecules absorbed. Depending on the magnetization direction of that substrate, you can either have plus or negative helicity spin polarized electrons, and these may interact differently with the L or the I R enantiomers. So the experimental setup that we designed was to first vapor deposit a molecule, L-histidine, and we used this one because it was well understood in terms of its interactions with surfaces, and we knew that we could deposit it reliably on the surface. And then we exposed those films of L-histidine to 695 eV soft X-rays that were generated by the Advanced Photon Source Synchrotron at Argonne National Lab. Those X-rays then interacted with our magnetized cobalt substrate to eject the spin-polarized electrons, and then those spin-polarized electrons could interact with and damage the vapor-deposited L-histidine. We can then probe that damage using a technique called X-ray photoelectron spectroscopy, and then determine how that difference in helicity affects the damaged cross-sections by reversing the magnetization of our substrate in situ. The XPS measurements look like is shown here, where I've focused on the nitrogen component of our molecules, nitrogen being very unique to the analyte molecule and also on the chiral center. So we see that the high-resolution spectra of nitrogen can be fit with 5 different peaks. The first 2, being the largest, are corresponding to the N1 and the N2 components of the neutral histidine molecules, while these smaller peaks out here, the N3 and the N4 peaks, correspond to nitrogens within the zwitterionic species. It turns out that these zwitterionic species are important because depending on the thickness of our sample, you see more or less abundances of those zwitterionic species. And so it turns out that for a thin film or a monolayer film, sort of corresponding to this 0.3 nanometer thickness, where the N3 and the N4 components of the zwitterions are hardly there, you get more strongly interactions with the molecules in the surface. Whereas with the thicker samples, those interactions aren't quite as strong, so that the presence of multiple monolayers can weaken the molecular interactions between the molecules in the surface, potentially enhancing any measurement of this spin dichroism effect. When we look at the abundance or the area of those peaks as a function of a radiation fluence, or the cumulative electron fluence that these molecular films have been exposed to, we see that they are well fit by exponential decays. So then these exponential decays can be used to give us cross-sections for the damage, or what is the damage cross-section for these molecules with the spin-polarized electrons. And so again, it turns out that the thicker samples, because there's more molecules there, and they're less strongly interacting with the surface, they give better and more precise exponential fits, which ultimately give us better statistics. And then we also see that it's pretty clear that the zwitterionic species, both in the thick and in the thinner samples, the zwitterionic species are damaged more readily than are the neutral species. So when we take measurements of these damaged cross-sections at multiple different spots on the same sample, so same deposition, different spot, we take about 10 to 15 different spots in both of the magnetization conditions, and then do a statistical comparison for those cross-sections measured in both magnetization conditions, and look for statistical significantly differences between those two populations. And what we see that, in fact, the total cross-section and the cross-sections for the zwitterionic species show strong evidence of spin dichroism, so that the dependence of the damage on that electron helicity for these L-histidine molecules. If we assume that the reverse is true for the D-histidine molecules, which can be expected from previous measurements, we get that if we had a racemic mixture of L-histidine on the surface, we would produce actually a 17% enantiomeric excess when only 40% of the original molecular population remains. So these are pretty strong effects of this spin dichroism that we're showing here. So in conclusion, we've shown that L-chiral enantiomeric excesses have been identified in many primitive meteorites, and although many mechanisms exist to explain these excesses, ultimately the cause of the symmetry breaking between YL versus D remains an open question. These experiments have shown that there are strong enantioselective preferences measured for spin-polarized electrons ejected from a magnetized substrate in their interactions with deposited L-histidine amino acids. It sort of remains to be seen how the spin-polarized electron these spin-polarized electrons can create these enantiomeric excesses within different molecular populations, and this is largely an unexplored mechanism within the field. So with that, I'd like to thank the people who helped me out with this work, Tom and Sermana at Georgia Tech and Richard at Argonne, as well as our funding from the DOE and NASA postdoctoral fellowship. Thank you all for listening, and I'm happy to take your questions online.